thank you. So today we will go further in the A infinity categories. And I would like to speak about twisted complexes. So remember that we started with Sm eta, a graded surface, and S, a full system of graded arcs on this surface, and from this data we can construct a A infinity category, curly AS. So it's A infinity category, and okay. So that was what we did on Tuesday. And the aim of this construction of twisted complexes is to, from A infinity category, how can we build a triangulated category? So the motivation is a triangulated from A infinity category. And once we have this, we will apply this to this A infinity category associated to the full system of arcs. So first remark, so remember that in general, already A infinity category is not a category because this mu2 is not associative. So already we start somehow, it starts to become difficult, but it's very easy to check that if A is A infinity, then I could define a category. H0 of A is a category. So I should define what I mean by H0 of A. So by definition, so the objects are the same. And the morphism they are given by the cohomology of each morphism complex. So just because if I have two objects in A, I can consider the Hom space of X into Y, and this is a K, a Z graded vector space, and I have mu1, and together with mu1, this is a complex of K vector spaces. So I could take the cohomology of this complex. So I get then this is just a graded vector space, and this will be the Hom spaces between my two objects X and Y. And for composition, I just take mu2. Mu2, but on this cohomology classes. And so the proof is, in fact, well, I just give you a hint of the proof. It's just that you need to prove that this composition is actually, you need to prove that this composition is well defined on cohomology classes, and that this composition is associative. So the idea is that if you have three cohomology classes, so they then live in the kernel of mu1. Well, you want to need to prove that A, B, C minus, or again, I have some sign issues, but we don't care about signs. You need to prove this, so that if you take, so this is really with a mu2 of mu2 of A, B, C, and the same here. But this is what you need to prove, and this is just the Stashev equation for n equals 3 gives you directly the fact that this belongs to the image of mu1. So then you have this associativity. So already it's good, because now at least we know how to build a category from a infinity category. But this is not what we want in our setup, because this A infinity category is very, very small. It has only finitely many objects and finitely many morphisms. So this is not the kind of triangulated category we want. So that's why we need this construction of twisted complexes.
Wasn't mu1 equal to 0 in our example?
Yes, in our example, mu1 is 0. So you're right. It means that, so in fact, in our example, so if mu1 is 0, so then the cohomology is not very hard to compute. Sure, I mean, this is equal to the home space. And in fact, so I could also take this together with mu2, and this is a category already. So, I mean, but this is not what we want. But
So this is already associative?
yes, it is already associative. Because if you just look at the Stashev equation for n equals 3 and you put mu1 to be 0, you get just associativity of mu2. So this is just for a general construction, because so what we will do is first build a very big A infinity category where mu1 won't be 0 and mu greater than 3 won't be 0. And then we will apply this construction. So this was just that you're right here in this already. I mean, this is already a category at this stage, but this is not the category we want. Okay, so the idea is really that if we start with A to be just given by a quiver, so I would just denote it like this: P1, P2, with some space of morphism of dimension 1. So we want to get this KB proj KQ, which is given by the objects. So remember, we have all the shifts of P1, all the shifts of P2, and also this complex and any shift. Okay? This is the object I would like to build from this data. So so here what we need to add is that first we need to add the shift of all the object of A, and then we need also to add some kind of cone of morphism or some complexes made out of these shifts. So the construction then goes into 2 steps. So first, we construct this category D of A. So it's not a category, it's a infinity category. But so the objects, they are, and we need, I mean, yeah, here I wrote an equality. This is not true, okay? I could take any direct sum of this object too. So maybe I should put some additive of this. Okay, it's much bigger, but so the objects here in this category will be just formal sums of formal shifts of objects. So they are finite. So here I don't know. No, they could be in different degrees. I don't know how to write it. Okay, maybe I don't write a big sum. I just start without the sum. It's better like this. Okay. So the object, they are things like this, with xi being an object in A, and li is just an integer. And the morphism, they are just the same morphism, but you kind of shift everything. So home between in ZA between xi li into xj lj will be by definition the home space in A between xi and xj. And so this is a graded vector space, and I shift it by lj minus li. So what does it mean? Just so concretely, what does it mean? It means that if you have, for instance, if you have so if I have A from x to y degree 0 morphism in A. So just to give you an example, so if I have a morphism of degree 0 in A, I get lots of morphism in this category, because for any L, I will get a morphism from XL to YL shifted by L. So with the same L, and this will be of degree 0. Again. So maybe I will denote it like this. And also, I will get for any M and N, or what should yes. I will get also a morphism from XL to YL plus M, and this one I will denote it by A shifted by M. So I will get a morphism like this for any M and L integer, and this will be of degree minus M. Okay, so just from one morphism I get lots of new morphisms. But this is, I mean, This is still quite simple. And for higher composition, so I need to define the composition. And the composition, they are, well, you can imagine what they could do. So then my morphism will be of this form. So here, I mean, there is really an abuse of notation, okay, because here I denote by A bracket 0 this morphism from any L. So, I mean, if I would be very rigorous, maybe I would put an index L somewhere, but then it just becomes very heavy. So I just denoted A shifted by 0 to remember that its morphism as, well, it has degree 0 because A has degree 0, but in general it will have the same degree as A. But I have lots of them. So here it's not really clear what I mean by this, but I mean, they should compose. So, I mean, the target of this should be the source of the next one, and so on, to make sense. And this is just, so here there is a big, complicated sign issue, but we don't speak about signs here. But then you can imagine that it's kind of easy, that this is just, and yes, and I need to put something here, some shift so that it works, but okay, this is just the formula. So it can be extended, and then this is also a infinity category with the structure. But this is not enough, because here we have added only the shifts, and we also want the cone, so we want all the complexes. So now from ZA, we construct this category of twisted complexes, twist of A. So the definition is quite technical. So the objects, they are given by pairs W delta, where so W is okay, so it's in the additive closure of this ZA. So it's a direct sum of this all these objects. And delta is a morphism in ZA from W to W of degree 1. And we also need some condition, so which is a technical condition. So we need two conditions, so such that first we can, so here it's a direct sum of shifts of object in A, and so there exists a decomposition of W as a sum of I equal 1 to n. So I put here some order. So then it should be I don't know, something like this, but such that delta is lower triangular when I decompose it into this So you will see in an example what it means, but it's just like, I see delta as a matrix, and this matrix should be strictly lower triangular or upper triangular, as if you want. And also we want some technical condition that the sum of on any k of new k of delta just 0 on the diagonal. And I also want this sum to be 0. So this is some technical assumption. I will just tell you in a minute why why we need this assumption. But this is something needed. Okay, so the objects are already quite a bit scary. We will see an example in a minute. And the morphism, they are not so scary because they are the same. They are the same. So the morphism between W delta and W delta prime in twist A, they are just given as the morphism in ZA between W and W prime. So, or maybe I should add of ZA, so I may have some direct sums, but this is not very, so it's just like here we can forget this delta. So this is okay, but it means that in general you will have lots of morphisms. But what is really new here is a higher composition. So here mu n twist A of something. So here I didn't write the shifts because they are somehow hidden in here. So here it's really scary. You do the whole sum of. So here I will add all the possible delta. So okay, here I go from x1 to x2. Here I go to xn minus 1 to xn. For each of these, I have some delta. Delta 1, delta 2, delta n. And I insert all this delta if I can. So some part of the delta. So it's almost impossible to write it in a rigorous way. So I'm just writing it like this. And here maybe I could add some deltas, or it could be empty also. But and here, of course, the power is as high as you can. Okay, so it's a super huge sum. So it means, well, it feels that it's impossible to do computation for this, but we can do in some cases. Okay, so just to come back to this remark, so this technical assumption, it's useful to prove that actually this sum is finite. Okay, so because a priori you get something infinite. Okay, you could add deltas as much as you want, but you want this to be a finite sum. Okay, so. Okay, so this category is A infinity category. So this is a theorem due to Seidel. So the proof is, of course, very technical, as you can imagine. And the good news is here that now if you take the H0 of this category, then you get a triangulated category. And this is the category we will look at now. And I just would like, so today I would like to show you that in this setup, for these very small categories given by a full system of quadratic arcs, this category is not that scary. Yeah, I don't know why, I mean, yeah, you take the full homology. So I don't know why, I mean, I didn't choose a notation. I find it also a bit strange that it's not with a star because, but yeah, this is what Seidel is using. So I'm just following. But yeah, I don't know why it's reason H0. Okay, so examples. So the first example is maybe I come back to my small quiver. So I take A to be this P1, P2. And let's say also I put like, yeah, the degree of A, I declare it to be 0. And so then, then one can check that this H0 of twist A will be this category of KB proj of KQ. Well, this works in fact for any Q, but just in this example. So here, so in the ZA construction, you will get this object P1 shifted by L and P2 shifted by M. And when you do the twist construction, then you get new objects, typically, which is P1 to P2. So that maybe you would like to write P1 plus P2 shifted by -1, or, okay, maybe I should do it this complex. So if I take 0 here, it will be more, so I put an equality, it would be P1 shifted by 1 plus P2 together with the matrix 0A. Okay, yes. And here I should put, okay, I rewrite it like this. Or correspond to the object. So it's P1 shifted by 1 plus P2 shifted by 0. And my differential is given by the two no, it's given by this thing. So A, so remember A here, I assume A to be of degree 0. So this one will be of degree, so it's degree of A minus 1, so which is 1 in this case. And this is what I want. I want my delta to be a degree 1 map. Okay, so this is and this is something that goes from P, so really A shifted by -1 goes to P1 shifted by 1 into P2 shifted by 1 minus 1, so which is 0. Okay, this is what you have typically. And in fact, so here, when you compute this twist A, since here I don't have any higher multiplication, I just have maybe some mu2, but that's all. Mu1, and I don't have mu1, I just have a mu2. In this formula, you can see that, I mean, for n bigger than 3, then this one, here the power, so it's j, I don't know, but j has to be at least n, because I have at least these n entries. So if my mu3, so mu3a here is 0, this implies that mu twist a is also 0. So then this is nice in this setup, because this category twist A is not that scary because it's just a DG category. You may have a mu1 and you have a mu2, but that's all.
Because in this case, you think that this A actually was the category.
Yes, A is a category.
So that's why there's no mu1.
That's why there is no mu1. I mean, mu1, it could be a category with a mu1, then it would be a DG category. But here you have just mu2, which is, so here mu I is 0 for I different from 2 in this situation. Mu2, well, you don't have so much, but you have that, I mean, you have a mu2 of 1p2 into A is A, for instance. You have this, still have mu2s. You have some multiplication. And in general, if you take a quiver, you may have several arrows, so you will have some mu2, non-zero mu2s. So and you always, I mean, mu2 is never 0 because I have some unities. So also this one is of course always equal to mu2 of 1, 1 is always 1. So mu2 is never 0. So, I mean, this example, well, it's a nice example in the sense that here we see that we recover the category we would like to recover, but then you may ask, well, I mean, this is a very scary construction, and here we have this KB proj, which may be a bit scary, but much less scary. At least we see, we have some control on the morphism and on the objects, so then what's the point of using all this? So that's why I give you another example.
In this first example, so twisted A is just the category of complexes? Or
Twist, no, it's a infinity category.
But with no
So in fact, so it's a DG category. It's a DG category, so you can check that this is. So you can take the category of bounded projective complexes, but you see it as a DG category. So meaning that in this, so, okay, so this here the objects, they are bounded complexes of projectives, and the morphism, they are not morphism of complexes. They are just morphism of graded spaces. And when you compute this H0, what you do is you take the kernel of the derivative and you divide by the image. And the kernel would be the commutativity, and the image will be the homotopy. So you just obtain what you want. So then, yeah, here you have some mu1, and the kernel of mu1 for morphism will be a morphism of complexes, and the image of mu1 will be morphism homotopic to 0. So then when you compute the homology, you get. What?
Delta, the mysterious delta over there.
Yes. So it's encoded in the object. So the object, they are complexes of projectives. So it means that you have. So it's really like this. So you think that P1 into P2, you think that, this complex, P1A, P2, it's really this object, P1 shifted by 1 plus P2 shifted by 0, with this delta being this matrix.
Yeah, but what is confusing for me, at least, is that on the one hand, the dimension is supposed to be the U, and on the other hand, it's supposed to be the delta. So I'm confused there.
No. This is a delta. So this is a delta. And here, in this category, so this is twist A in that case. In this category, you have a mu1, but the mu1 is really eating some morphisms. Okay, so it's not, delta is the differential between objects. Delta is a map. Mu1 is a differential that eats map, right? Mu1 goes to xy into xy. Okay? It's really technical and a bit. So now I take a more interesting example. So I come back to my colors. Yeah, maybe I just need this. Okay. So example 2. So I will just now take this. Okay, so I have this square. So if you want, it sits into a disk, or it could be just maybe I could write it like this. I'm just, okay, I take a, can you see the green? My green is maybe, okay, these are, my boundary segments, and these are my arcs. What? I have my 4 arcs, and remember that, we could choose some grading so that, okay, I will give some names here. So this is A1, A2, A3, A4. And this one has degree 0. This one has degree 0. This one has degree 0. No, sorry. I would like better to put degree 1 everywhere, and here it's -1. So you remember we had this example. I mean, you can put the degree you want, but what just you need is that the sum should be 2. So this is something that we can't avoid, but we could choose a gradient so that we get this. Okay, so this is my category A of S. And remember, we have some mu4, which is non-zero. So this mu4 of A4, A3, A2, A1 is non-zero. So now in twist A, I can construct the following object. So I take x1 shifted by 0 plus x2 shifted by 0 plus x3 shifted by 0. So this I will denote by y, and my delta is given by a matrix, 3 by 3 matrix, which is A1 shifted by 0, A2 shifted by 0. And so this is my delta. And this, so since A1 and A2 have degree 1, then my delta has degree 1. So that's okay. It fits, and I get a strictly lower matrix, a triangular matrix here. And well, this condition I don't check, but I mean, this is somehow clear that this would be 0. Okay. So I have this object. So this is my y delta. Now I consider another object, which also is in my category. It's just, so maybe I call it, it's just the object x4 shifted by 1, with a 0 differential. So this also lives in twist AS. And now I would like to just, okay, maybe for some notation. So instead of thinking as y as this, I would rather think as y as a complex. So I will denote it by and here I put A1 shifted by 0, A2 shifted by 0. So I prefer to write it like this. So if I would have something here, so I mean, it's not a complex in general. So here it looks as it was a complex, but I mean, I could have something non-zero here, then I would get maybe a map like this. So it's not in general, but it's just a way to think about this object. So it's much easier to think that this object is like this. And I want to compare these two objects in the category H0 of twist A. So the fact that, so here mu2 of A1 and E2 is actually 0, so that's why we have this condition, in fact, here.
What you're saying is you have something that's not a complex, despite the fact that
you could have something like this, and then you have to, we will see another example where we have something like this. Okay, so now I want to compare these two objects. And I have some morphism from these two objects. So the first one, I call it F. So it goes from, okay, yes, it goes from x4 shifted by 1, 0 into y delta, and it's given as follows. So I mean, I don't have so many possibilities here, but I have a morphism from x4 to x1, which is given by a4. So now I have to be careful with the shifts. So it's a4 shifted by minus 1, no, by 1, or no, by minus 1. Okay, it's a4 shifted by minus 1. And what is the degree? So the degree of a4 shifted by minus 1 is supposed to be the degree of a4 minus 1, which is minus, oh yeah, it's 0. That's okay. So it has degree 0. I have this morphism F. And so the first thing so this morphism, it lives into twist A, but we want to understand this morphism in H0 of twist A. So first we have to check that this defines a non-zero element in, so we have to check that it is in the kernel of mu1 and it's not in the image of mu1. So it's really a morphism. So check that this morphism belongs to the kernel of mu1 twist A, and it's not in the image of mu1 of twist A. So I let you this as an exercise, but this is this is not really complicated because, the fact that it's in the kernel of mu1, it really comes from the fact that if you do mu2 of these two, you get 0. So it's really, you can really think that you want this to check that this square commutes if you want to be in the kernel of mu1. And this square commutes because the composition of these two is 0. So you want this to be a morphism of complexes. And now you want not to be in the image of mu1, and it's just because, well, here this is non-zero, so it cannot factor, this one cannot factor through 0. So it's clear that it's not in the image of mu1. So this is the idea. But so what I would like to show you, or at least to give you an idea, why is F will be an isomorphism in H0 of twist A. To prove that it is an isomorphism, I should find the inverse map. And the inverse map will be given by some G from Y delta to X4 shifted by 1, 0. And so here, I'm just taking, okay, maybe I write it here. And what could I take? I don't have also many choices. I could take A3 from here to here, and I have to shift by 1. Okay, so now I have that this map, this G, is the degree of A3 minus 1, which is 0 again. So it's a good, I mean, if I want these two maps to be isomorphisms, inverse to each other, I mean, first they should be of degree 0, because my mu2, mu2 is a degree 0 map, so if it eats something of degree 0 and something of degree 0, it gives me something of degree 0, and identities are some 0 maps. Okay, and now you can check the following, that mu2 in twist A of Fg is again, up to sign, the identity of, I started with G, so it's the identity of Y delta, which is really the identity of x1 shifted by 0 plus the identity of x2 shifted by 0 plus the identity of x3 shifted by 0. And we also have the fact that mu2 of gf would be the identity of x4 shifted by 1. Okay, so again, it's an exercise, but I just give you an idea why it should be true, because we can really wonder how it works. So what I could do, okay, maybe I write here my x4 shifted by 1. Here I have so maybe in this picture I will write my so here is A3 shifted by 1, and here is A4 shifted by minus 1. This is my morphism. This is my F and G. I write them in blue, and maybe I write in red. These are the deltas. So here I don't have any delta. But then when I compute mu2 of this, so mu2 of Fg, if I use this formula, so I could compute mu2 of A3, A4, but this is 0. So this is mu2 of these two, but this is 0. But what I can do is that I put deltas wherever I could. So, for instance, I could do, so here I could do mu3, for instance, of, so I need still to have A3, A4. Maybe I should write them in blue. And here I could add some delta. And what is my delta here? My delta here is A1. So I could put A1 here. I have some shifts, but I don't write the shifts anymore. Okay? This is part of this sum. But this is 0, so once again, we can forget it. But here you can see that maybe I could add another delta, this one, and put a 4 here. And now I have something which is not 0. And what is this? It's just the identity of x2, x3, this mu4. So this is the identity of x2. And I have two other mu4 that gives you my two other identities in this sum. So this is how it works. And a priori, I could have several other, and I could also put some deltas here. Okay, I mean, I could take, for instance, I could take delta of this, 1, 2, 3, 4, and this is non-zero again. So this is where you get these identities. And this is how you check that this composition is actually.
Yeah, so in order from one,
It's just in the definition of this category. We have that mu2 of A1, A2. They do not compose because they are not on the same. It's just in the definition of A. Okay, so what should I say now? I don't know. I have half an hour left.
What's the conclusion of this?
It just, okay, the conclusion is that in H0 of twist A, the object, this object Y and this object X4 shifted by 1, they are isomorphic. Okay, maybe I still, I mean, I don't have so much time, but I give you maybe another example to show you what kind of other complex we could obtain. So here, I mean, something, other exercise, you can check that. If I take the complex given by x1, x2, okay, I don't put shifts, but you can find the good shifts. This is isomorphic to the complex x3, x4. Up to shift, if you find a good shift, so that you make them isomorphic. So this is with A1 and this is with A3. So it just to also to show you, I mean, in this category twist A, you have really lots of objects, lots of morphism. But when you take H0, well, lots of objects become isomorphic and you have much less morphism. So this is somehow the morality of this. So just take another example with a more complicated surface. So I take the cylinder. Okay, so here I will put my thing like this, and I take this arc that I call x0, and now I want to so this will be x1, and I take another one here. This is x2. Okay, so maybe I would rather draw my picture like this. Okay, now I have to, So this is my picture. I have to define the line field on this cylinder, and for this line field, well, I have some different possibilities, and I could take the horizontal line field. Okay. So this is eta is a horizontal line field. So now other exercise, you can check that we can find grading on this curve so that so I have morphism like this. And I could take degree 0 here, degree 1 here, degree 0 here, degree 1 here. I mean, the sum should be, the sum has to be 2 again. But here we have another constraint because x0 is here and here. So once I have chosen my angle here for x0, well, now it's fixed. So if I force this arc such that this is degree 0, then this one I don't have any choice. And this one will be of degree 1 in this example. So you can check this. Yeah, okay, I did it well. So now I can look at, for instance, this complex. So here, okay, this is the row of degree 0. Maybe this is A0, A1, B0, B1. Okay, so here I could take A0 shifted by something. It is of degree 1. So shifted by -1. And here I take x0, the map from x1 to x0 -1. And here it's A1 shifted by 0. It's a degree 1 map. Okay, so I mean, this is the same as before. It's an object in my category twist A. But here, I have some morphism from here to here of degree 1. I have 1 x0 shifted by -1. This is a degree 1 morphism. Okay, from x0 to x0 shifted by -1. So this one has degree +1. And so now I would get a triangular matrix with the three entries non-zero. And in fact, I could sort of put a parameter. For instance, here, I could take lambda in C star and multiply my identity by some integer, some scalar.
I think if you put lambda equals 0, then it's not, it won't respect the sum of the k equals 0. So it's not an object.
No. I mean, I could put lambda equals 0 and I get an object. Yeah, it's still an object. But with lambda non-zero, it's also an object. And they are going to be different. So what you can check is that this object, so maybe I give it a name, so B lambda. So B lambda, yeah, so if you want, I could put lambda to be in C. So I allow lambda to be 0. So B lambda is isomorphic to B mu if and only if lambda equals mu. Mu is maybe not a good lambda prime. Okay, so I get different objects for each of these parameters. And what also you can check, another small exercise, is that these parameters still I could move. So B lambda is isomorphic to So here I put identity, but now I put lambda minus 1 here of A0. I could sort of move my lambda to the next arrow, and then I have an isomorphism. So again, I mean, all these isomorphisms, they are in H0. To speak about isomorphism in an A infinity category, it doesn't make any sense, because there is no, I mean, it's not a category, so there is no meaning of being isomorphism. But in H0 of twist A, then we have this. So here, with the same example, I could do something else. I could take the same surface, the same and now okay, but now I take a different line field. And what I could take for a line field would be something, so I'm just like drawing the foliation of this line field, but I could take some line field doing like this. So if I take this line field, you can you will have, for instance, that so here it would be 0. No. Yeah, it could be 0, 0, 1, 1. So this is something you can check if you have a different line field. And so here, then, so you still have this x0 goes into x1, goes into x2, or goes back into x0. But here, if you start with x0 shifted by 0, if I go that way, I will end up with x0 shifted by 0. Or no, if I go that way, for instance, if I go that way, I will end up with shifted by 2, minus 2. Well, anyway, so I have this thing, but here, so now, I mean, I don't have a map. I have a map here, but it's a degree 2 map, so it's not a differential in the sense of twist A. So this one is an object, but I cannot do the same construction as here. And here it's really because here the sum of these 2 degrees is 1. And what you can check here, it's like, so here it's a case where we have some non-trivial loops, closed curve on this cylinder. So you can just so there is the pi1 is so here is, I have some generator of the pi1, and you can check that in this situation, the winding number of this is 0. So the winding number of this curve is really, you follow, so my curve is here, and I follow the line field along the curve, and I count how many half term I do. And here I do 0 half term, so the winding number is 0. Here, if I take this one, well, here I'm just like this, and then I do 1 half term. So then here the winding number of this curve is, well, plus or minus 1. It depends on the direction of the, I have to orient my curve, but it's non-zero in any case. So I just a remark about this example. So now I come to the main theorem I would like to present. So
Just to understand what you say more or less is that to gamma you're assigning one of these objects in this state.
yes, so in fact, so I hope I will have the time to state it, but the objects in H0 of twist A, they will be in bijection with curves and with closed curve of winding number 0. So in that case I don't have any. In that case I have some objects, this object. So here, of course, here I have this object and this, but here, like twist A, it's much, H0 twist A is much smaller than here. I have less objects.
Maybe this relatively set or an indecomposable object.
Yes, indecomposable object.
So say this indecomposable object.
This one is indecomposable.
Twist A are in bijection with what?
I will state it later. I mean, it's just, yeah, hopefully. I hope to have the time. Okay, first let me state the theorem by Haiden, Katzarkov, Kontsevich, that if I take two, so I start with a fixed graded marked surface, and I take two full system of graded arcs, then there is a canonical triangle equivalence from H0 of twist AS into H0 of twist AS prime. And okay, so what is the idea here of the proof is that the idea of the proof is that if you start with two full system of graded arcs that are included into each other, so if S is included in S prime, so that could be the case because, okay, remember that I could take in my square picture, this is a full graded, a full system of arcs, but I could take this one also. It's a full system of arc. So this is typically the situation where S is included in S prime. So if S is included in S prime, then of course I have a nice embedding of A infinity categories. And these embeddings give me, so here it's not that obvious, but this is due to Zeidel's construction that it induces also something like this. And which is an equivalence when you take the homology. And this gives you H0 twist A S into H0 of twist A S prime. And this is, so why do we have this? Well, this is because typically here, this new object I had, okay, so this is S. This is S, this is S prime. And well, in this category, we can check that this arc is isomorphic to this complex. Okay? Like in your picture here, if I take the complex, this is my exercise. Yeah, this one. The complex going from x1 to x2, it's isomorphic to the complex of, or or it's also x4 it's just the thing before. But this one would be, if I would add this x0, there's a diagonal, then this complex would be isomorphic to x0, x0 being the diagonal. So here I have lots of objects that become isomorphic. And so this diagonal somehow, it's useless in this category because it's already appear as a complex. Okay, so this is the first step of the proof to understand that each inclusion gives you an equivalence. And now what you can do, I mean, if you start with two systems, what you can do is you take the first system, you complete it into a triangulation. So I get something like this. I take the second one, I complete it into a triangulation. I get another equivalence. Now I have two triangulations, and I know that I could pass from one to the other by doing flips. And flips is just something like this. I mean, a flip, you can see it not as a flip, but if I have some system like this, I mean, I have an inclusion like this, I have an inclusion in the other direction. And this gives me equivalences, so a flip gives me an equivalence. So this is the idea of the proof. So it does not really prove that this is canonical, but at least it gives you how to build such an equivalence. And the other thing here, which is very nice, is that because of this construction of this equivalence, if I start with, so I start with a graded arc. So if it's simple, then to this graded arc, I can see it as an object. I mean, I can complete this into a full system. And then, so this graded arc give me, it gives me an object in H0 of this full system. And then it means that if I would have complete into another full system, I will get the same object through this equivalence. So it means that, so now we can, because this equivalence is canonical, we can really speak about this Fukaya category just depending on the surface with a graded field, with a line field. And in this category, any simple graded arc gives rise to an object which is well defined. And so it does not depend on the choice of the full system you embed to. So any graded arc gives rise to an indecomposable object. And in fact, there will be more objects, but this is the idea of okay, what I have, how much time you have left? We started a bit late. What? 10 minutes, okay. So now, okay, I will finish by okay, so now I come back to this example, and here, so we have seen that this complex is isomorphic to this object, and this object, it corresponds to a graded arc. So somehow we could think that this object is useless. We don't need this object in the category because it appears in twist A as a complex. Okay? So this is the idea of what we will do now. So maybe I just keep my picture. I don't know where I am here. So I will speak about dissections. So definition. A dissection D is a collection of simple graded arcs on S M eta such that so it's the same kind of thing we have. So I want them to be pairwise non-isotopic and pairwise non-intersecting. I don't want intersection. And I want that, okay, so here, x1 up to xl. And now I don't ask all the boundary component to be, all the boundary arcs to be in my dissection, but I just ask that S, it cuts out my surface into the union of, is a union of disks with exactly one boundary segment. So it means that the picture is typically like this. So here I have a boundary and my collection of arcs cuts out my surface into pieces like this. So just as a remark, if I add this one, then I get a full system of arc. But I just don't want to take it. So just very few examples. So I take my square again. I could take this, or I could take this. This would be dissections. If I take my my cylinder, so maybe I will use some colors. I could take this, or I could take something a bit different, something like this. So these are dissections, and it's not hard to check that two dissection has always the same cardinality. It's just a computation of Euler characteristic. And so from a dissection, what we could do is the same game. We could, so I mean, D is like, if I add this boundary arc, I can embed my dissection into a full system. And I can look at the A infinity subcategory of AS generated by the object of D. And here, what happens in this category is that in this category, so there is no higher mu. So the mu1 is 0, of course, because it's the same mu1 as this one. But there is no higher mu because I don't have some polygon, a complete polygon. So it means that this is a nice situation where I have a category, a graded category. So here, for instance, I could, for instance, take this one, and then it's really, okay, so this category would correspond to the category of the quiver with 3 vertices and 2 arrows going like this, and with the composition of these 2 arrows wouldn't be 0. In this situation, I would get the category given by this quiver, but here I ask BA to be 0 because the composition is supposed to be 0. Here I get this one. And here I get this one. With no relations. What?
When you say I get this quiver,
yes,
what does it mean?
I mean that AD is the same as, so it's a category because I have no mu3. So AD is really the category. I mean, it's really the category of projective of some quiver modulo maybe some ideal of relations. And in fact, again, using the same argument as before, like the fact that its x4 is useless, we have the fact that H0 of twist AD is equivalent to H0 of twist AS, given, so this equivalence given by the inclusion of the collection of graded arcs. And so, okay, and this one is KB proj KQ over I. So for some quiver Q and relations I. And this is, so this kind of algebras that appear here. So here, I mean, yeah, I should add it. It's a graded quiver because in general I may have some degrees here, and this is of importance. And then, so if I have a grading on my quiver, I mean, if it's not the degree 0 everywhere, then I need to be careful here. It's more like the derived category of this algebra seen as a DG algebra with 0 differential. But okay, it just, I can write it like this, I think. And this KQ over I, these are what we call in my field gentle algebras. And so they are well studied. So they come, I mean, it goes back to, so they were introduced by Assem and Skowronski in '87, so already a long time ago. And they have been studied really a lot. So, I mean, lots of things are known in representation theory about this algebra, about their derived categories, their module category, and so on. It has been studied by many people. And so then the corollary is that this Fukaya category of S is the derived category of some gentle algebra. And I mean, here what we get is a gentle algebra, but I didn't give you the definition of a gentle algebra, but there is a definition given by these people, and all gentle algebras arise in this way. So this is really, they are the good of some gentle algebras. And yes, so maybe I should stop here, even if I didn't speak about the object, but I will tell you tomorrow the answer to your question.